Have you ever seen a bridge collapse on TV or heard about it in class and wondered, what are the different parts of a bridge and how do engineers design a bridge to keep me on it? Well, today we're going to talk about how bridges are designed and the ways engineers make sure bridges stay up and continue to be used for many, many years. So, today we will cover the different parts that make up a bridge and help keep it up, the ways engineers design bridges, and we will also briefly analyze bridge designs in the past to see what is considered when creating a safe and usable bridge. Let's get into it. First, there's a question I have to ask you all. How did you get here today? Did you happen to cross a bridge? So maybe you drove or someone dropped you off, but what would you have done if there was no bridge? Would you have to take a boat or take a longer way to get there without the bridge? Bridges are really important. Also, did you feel safe when crossing the bridge? I personally have to cross a bridge to get to school, and I've driven over it so many times, I hardly think about it failing. Let's look at the different parts of a bridge engineers consider when designing and building. Superstructure is the part of the bridge that provides the horizontal span, like in this picture. In other words, they are the members that span the gap and get loads like cars from where they start to the substructure. The superstructure is usually comprised of the bridge deck, girders, truss elements, and other things. Next is a substructure. This is the part of the bridge that supports the superstructure and transfers the loads from the heavy vehicles and such into the foundation. These are usually comprised of pier caps and piers. After that, the foundation takes the load down into the soil. Each part of the bridge plays an important role in getting loads from where they originate to the earth. Engineers call that the load path. Each of these three components has to be a critical link in the load path chain. Let's dig deeper into the foundation. Get it? Dig deeper into the foundation? No? Okay. Anyways, foundations support the bridge. They take the load path into the soil or the earth. One type of foundation is a spread footing. This is a wide, flat foot that spreads out the load so that the soil can carry it and so that there isn't too much load on just one spot. You can think about it like snowshoes. The load from our body is spread across the shoe compared to wearing heels. This foundation is generally only used on very strong soil, like rock. For softer soils, piles can be used. These long, slender members get buried into the ground and use the end-bearing resistance, as well as the shear resistance along the sides of the pile, to get the loads into the ground. So basically, piles help support the bridge, so it doesn't slide, and also provide support up and down. For the largest piles, drilled shafts can be used. These can be 12 feet or more in diameter. Drill shafts go into the ground by soil being drilled out, a steel reinforcement cage being put in, and then concrete for a really strong foundation. The foundation may be connected by pile caps. The combination of piles and the cap form the bent, or the support locations for the bridge structures. Here's some pictures of the construction of the new I-70 bridge over the Missouri River. Really big augers that are 11 feet in diameter are used to bore a hole into the ground. Then a reinforcement cage is placed in the hole and it is filled with concrete. Finally, a pier cap connects the two drilled shafts in the bent. So next are the substructures, which are what connects the superstructure to the foundation. It is formed of abutments, which are basically structures that support lateral pressure of a span, especially at the end of a bridge, and hold back the soil at the sides, sometimes using wing walls. The substructure is also the bridge piers, or columns, that give the bridge the needed height for traffic or water clearance. And the pier caps are the tops of the columns that connect all the piers and provide the support for the bridge girders. Let's take a look at these pictures of the new I-70 bridge. These are really good examples of abutments, piers, and pier caps. The abutment is at the end of the bridge and has a wall that holds back the soil as well as places for the girders to sit. And that picture shows the pier and pier cap further along in the bridge.
Also, if you look inside the pier cap, it has lots of reinforcement to support the heavy loads of the bridge. Now, let's move on to superstructure. The superstructure is what bridges the span between the piers. The parts of the superstructure depend on the type of bridge. So first, let's take a quick look at the bridge types. There are beam bridges, which are one of the most common types of bridges today, because they can be built quickly with only a few connections to make. Beam bridges usually consist of a girder supported at either end, which are the horizontal beams that support the deck. Most bridges will have girders. In beam bridges, the girder is the only load-supported member, while other bridges use other members. There are also truss bridges, which use triangles to create a bridge that can be very long and stiff. Next, there are arch bridges that use the arch shape to resist load. And for even longer bridges, cable-stayed and suspension bridges use steel tendons under tension to support the span. Once the horizontal span is supported, there needs to be a deck or roadway, which is the surface the cars and trucks drive on, as well as barriers so that they don't drive off the bridge. The deck is usually made out of asphalt or concrete. As for the barriers, those are usually made of concrete or steel. There's one more part of the superstructure you probably don't think about, but they're called expansion joints. These are important, as in long bridges, there is a lot of horizontal movement, simply from the heating or cooling of the bridge. Kind of like if you've ever seen cracks in a sidewalk or on pavement. The expansion joints allow for horizontal movement without causing additional stresses in the bridge.
These stresses can cause problems when designing and constructing bridges. Speaking of, let's get into how engineers approach bridge design and main factors that come into play. Engineers are always improving bridge design, and with that, there are requirements, like the bridge has to be stiff and strong to carry loads like cars and trucks without the bridge bending. There are also codes and standards that have to be met when looking at the materials that are used to build the bridge. Engineers are able to calculate how much weight will be on the bridge based on standard design loadings. There are usually charts and calculations involved in this process. Engineers also look at the strength of the bridge. The stresses in a bridge can be determined using structural analysis and material testing that shows them how strong or stiff the material and bridge are. Here's a video of material testing with a concrete cylinder.
Next, let's talk about what constraints engineers have to consider when designing or redoing a bridge to make sure that the bridge is safe. Here's a list of the different design constraints. There's deflection, deterioration, foundation, use, and unexpected design constraints. In the past, there have been problems with the design of some bridges. This is due to constraints that weren't fully considered. By looking at these past bridges that were not designed correctly, engineers can improve those designs and always make sure that safety comes first.
The first design constraint is deflection, which is where the bridge bends or deflects too much and becomes unusable. Here's an animation of what it would look like if you crossed a bridge with a deflection failure. This bridge bends too much when the car passes over it. For a real-life example, here's a video of the Millennium Bridge in London. The bridge was designed to be a pedestrian bridge across the Thames River, but when people walked on the bridge, it moved significantly. The movement was primarily side to side because the people walking on the bridge locked into the slight horizontal movements of the bridge itself and started walking with more side to side movement in time with the response of the bridge. This caused resonance that made the movements even greater. Bridges have been designed with vertical pedestrian movements in mind before, but the horizontal movement of the Millennium Bridge was new and unexpected. To fix the bridge, engineers put in more horizontal members that lessened the bridge movement. So, What can we learn from the Millennium Bridge? We can learn that it's important to pay attention to deflections and vibrations in a bridge, even when it's unexpected. Next up is deterioration constraint, which is where the components of the bridge deteriorate or weaken over time. This bridge deterioration or weakening over time results in a loss of strength of the bridge. Deterioration or corrosion of bridges is a problem many engineers face in Missouri. The freezing and thawing temperatures, in combination with the road salts, lead to corrosion of the steel reinforcement in reinforced concrete bridges. This picture shows the underside of a particularly corroded bridge. Corrosion starts at the reinforcement, and over time, corrosion products build up and crack the concrete. This usually leads to posting or restricting the weight of vehicles that cross the bridge. If bridges experience erosion, this picture shows what happens. Engineers try to avoid this from happening by making sure inspectors monitor the corrosion, and when it starts to compromise the structural strength of the bridge, that the bridge is either repaired or replaced. Sometimes corrosion occurs when it's hard to spot and it becomes too late. This picture on the right is a pre-stressed concrete girder bridge that has experienced corrosion in the pre-stressed tendons, which went unnoticed until the girder failed. So, what can we learn from this design constraint? We can learn to use maintenance and inspection to prevent deterioration and, when needed, repair and replace bridges. Moving on, there's also foundation design constraints, which is where the foundation of the bridge cannot support the loads. This can happen a lot when water washes out the foundation. Take a look at this bridge. What do you all think is wrong with it? If you said something that has to do with the foundation, you're right. This bridge was sagging due to its foundation. The stream bed was slowly eroding or washing away the foundation, which ultimately may have reduced the strength of the foundation. At that point, engineers have to take into account how the foundation of the site may change with time. The foundation can change pretty quickly when water is involved. So what can we learn from foundation constraints? We can learn to analyze the foundation before placing a bridge and using the results to predict how the area will change over time to ensure it will be strong enough.
Bridge designs can also have constraints because they are simply no longer available to serve their purpose. This is called a usage constraint. In some cases, the deterioration of the bridge has led to posting or restricting the weight of trucks that can cross the bridge. And in other cases, there are daily traffic jams on a bridge when it is too small to carry the traffic that it demands.
So, what did we learn from this constraint? We learned to take more time when designing a bridge and think ahead so its lifetime is longer. Problems with being able to maintain a bridge are a cause for replacement. Let's hear from MoDOT bridge engineer Brandy Baldwin to understand why the I-70 Rocheport Bridge needs to be replaced.
Why do we need a new bridge over the Missouri River? So we need a new bridge here over the Missouri River because this structure that we have existing is aging, and it does need some new work in the very near future. So we're trying to get it done before we need to do that work. That work that we needed to extend its life cost about $30 million and was only going to get us about 10 more years. So we took that money and put it into this new bridge, and we're getting a bridge that's going to last us almost a century. So we're pretty excited about that.
Now let's move on to the last main cause of a bridge design constraint, which is an unexpected constraint. All the cases mentioned previously can generally be noticed and dealt with, but in some cases, unexpected constraints do occur and cause problems on a bridge. The causes can range from flooding, impact, overloading, deterioration, or design errors. Let's take a look at some of these unexpected constraints in more detail. Starting with hydraulic failures. These are constraints due to flooding. This bridge had the abutments and interior bends undermined as a result of floodwaters in 2019. So, what do you all think the major takeaway is? The major takeaway is to try to keep bridges out of floodwater to begin with, or make them strong enough to withstand flooding conditions.
Next is overloading or impact constraint. Bridges are designed to carry trucks of a certain weight, but sometimes truckers or farmers load up too much and overstress the bridge. Other cases of overloading are due to accidental impacts, usually attributed to trucks hitting the bridge. The steel girder seen here was severely twisted due to an overheight truck impacting the bridge. This next picture shows a truck that struck another bridge. The truck hit a bridge pier, severing it. And this last picture shows a truck that damaged a bridge girder upon impact. Here's another impact where the truck sheared off the bridge pier.
Usually what ends up happening to these bridges is engineers thoroughly examine the damage and make sure there is no traffic crossing the bridge while it's damaged. Sometimes the bridge can be repaired, sometimes the bridge needs to be replaced. It just depends on the severity. Let's think about what we've learned from these overloading and impact constraints for 1 second. So, we learned that trucks are very big vehicles that can hit and damage bridges, and in order to counteract this, we need to provide clearance and barriers if possible. Next is deterioration or corrosion failure. This is the Silver Bridge over the Ohio River in West Virginia, and it collapsed in 1967 under the weight of rush hour traffic that resulted in 46 deaths. The bridge was carrying heavier loads than it was designed for, but also part of the reason for the collapse was a defect in an eye-bar of the suspension chain. These chains were non-redundant, meaning if one failed, then the load could not be redistributed elsewhere. So, what do you all think we learned from this failure? We learned the importance of bridge inspection. The collapse led to increased focus of inspection of bridges. Another example of corrosion is the Mianus River Bridge in Connecticut that collapsed in 1983. The design used a pin and hanger assembly to support the spans yet allow for ease of construction and horizontal movements in the bridge. The drains on the bridge were plugged, allowing water and debris to drain on the pins. These eventually corroded and failed. Again, because the design was non-redundant, once a pin failed, the entire span failed. So, what lesson did we learn? We learned to avoid designs that are non-redundant and make sure critical locations on the bridge can be inspected. And a fun fact, the difficulty in inspecting these connections has led to their discontinued use. Let's take a look at a few more bridge collapses. This one happened in Minneapolis on the I-35 bridge. The bridge was built in 1967 and consisted of a truss bridge made of two main trusses that spanned the Mississippi River. This is a diagram of the truss. Be sure to pay attention to node 10. On August 1, 2007, the bridge collapsed, sending 111 cars into the river, and the steel bridge used gusset plates to connect the truss members. An inspection in 2003 found that the gusset plates were bowed, but engineers thought the bend occurred during construction. However, a design error in the gusset plates left them thinner than they were supposed to be. In addition, construction work on the bridge and a concrete topping slab put more weight on the bridge than ever before. The result was buckling and fracturing at node 10, and ultimately the collapse of the bridge. We learned not to assume that a component is strong enough. We should double check and even triple check designs. The last example is of a bridge in Tacoma Narrows that was built in Washington State in 1940. The suspension bridge supported two steel plate girders on either side. The bridge was very flexible and was nicknamed Galloping Gertie due to its movements. On November 7th, on a particularly gusty day, the vibrations became too much and the bridge collapsed. The cause was aerodynamic flutter, or the action of the positive and negative wind vortices on either side of the bridge. The same reason you may see a strap flutter in the wind. Today, bridges are designed with aerodynamics in mind. From this failure, what do you think can be learned? We learned that wind is really important and that we need to design a bridge shape that can withstand substantial wind.
So overall, bridges are safe. Although these are just a handful of hundreds of thousands of bridges out there with failures, most bridge failures are not catastrophic, and the bridge is closed and repaired before failure can even occur. Also, a lot of these failures happened centuries ago, and since then, engineers have created new technology and have learned from past mistakes to make bridges even safer. Safety is now a #1 priority to engineers when designing anything, and especially bridges.
So, after watching this presentation, you may be more interested in a career in engineering. If you like solving problems, being able to improve certain things you use and how you use them, or if you think outside the box, engineering might be for you. Other skills that engineers possess include coming up with improved and innovative ideas, being able to communicate and work well with others, and also being a natural leader. Who knows? If you become an engineer, you might be able to come up with an idea that can completely stop bridge failures from ever happening again.